I'd like to welcome everyone here, and hopefully we'll have a lively discussion. My name is Russ Butler. I am a marketing manager in the software and services group within Intel. And some of the things that you might have been aware of, that you might have seen lately is the, we'll go through, tweet to win a free Intel compute stick or SSD. Anyone tweeted yet today? No one. You know, when I sometimes work with developers that develop apps for Android or Windows or RealSense, and when I ask that question, like everyone raises their hand, right? So, and I did meet a few people today that I did remember meeting one person who doesn't even have a cell phone, which is cool. I'm like, wow, that's pretty amazing. But yes, if you do have a smartphone and you do have the desire, please do send a tweet and use the modern code hashtag. You can win some potentially valuable prizes. Let me show you a little bit what these are. This is a USB charger. You plug one end into the USB, and then the other will actually charge your phone. And this is a Swiss Army brand of it. So show us your tweet, and we'll give you one of these. This will get you through TSA as well. I know one of the panelists has something that won't get through TSA, which is just a pocket knife, but this one will. So I'd like to encourage you to do that. Also, at about 4 o'clock, Mr. James Reinders will be announcing the winners of this tweet challenge for today. One of the winners will win an Intel compute stick, which is a really cool piece of hardware. I'm going to show you these real quick. So this is an Intel compute stick. If you want to see an example of that running, come to the Modern Code booth. That's in the sponsor showcase right as you go outside. Also, we have an SSD that we're going to be giving away as well. So,
any chance this is multi-core?
It's an Atom. I don't know if it's multi-core or not. I think it might be a quad-core Atom. So.
No, IBX 512. Huh?
All right. So let's get into our discussion today, and we're hopeful to have a really good discussion.
It's a quad core. You're right.
It's a quad core.
Parallel processing on it.
Look at that. All right.
All right, I need one now.
So we're hopeful to have a really good discussion today with our black belts. Anyone know what a black belt is? Anyone familiar with the black belt program at Intel? Some of these are. We are in the presence of 4 black belts. Essentially what we have with the Intel Developer Zone, that's an online community as well as a program where we go out and visit with developers and engage with developers like you. And the more that you contribute to the Intel Developer Zone, you can earn status and become eventually a black belt. We have over 5,000 to 6,000 people each year that contribute to our communities, and we still have about 50 black belts, so it's a pretty exclusive club. We fly them to IDF every year, to the Intel Developer Forum, and we have some other benefits for them as well. So I'm going to let them introduce themselves. But we're really privileged to be here with you today, and we hope we have a really good conversation. So let's start with Tom. If you could, everyone just introduce themselves and tell us a little bit about yourself and the type of programming you're doing here.
Microphone. Pass the microphone.
My name's Tom Murphy. Matt and I were the first 2 academic black belts. Matt's from a Tier 1 school, and I'm from a Tier Infinity school. I teach at a community college in California. I became a black belt because I was helping to push parallelism in the universities by having a Teach Parallel broadcast. Paul Steinberg and I did that, and we'd interview people and try and move things in that direction. So it was kind of cool. And then I also, during the summers, would teach faculty how to do parallel and distributed programming, because I'm part of the working group for the National Computational Science Institute.
And I'm Matthew Wolf. As Tom said, we were the first academic black belts that were brought into the program. I work at Georgia Tech. I also have a joint appointment at Oak Ridge National Lab. So there's one part of the things that I do with Intel, which is all around parallel curriculum, parallel student engagements that may be extracurricular, doing hackathons and other sort of kind of deep immersive events. And then there's the other part, which is there are a bunch of 100K plus core machines that it's kind of fun to play with and figure out how to make codes run well and figure out how to make I/O work well and all of those sorts of things. So between those two, I cover a fair gamut of the code modernization space.
Hi, my name is John McAlpin. Just realized I've been doing HPC for 30 years. New black belt, though. I'm currently at the University of Texas at Austin, the Texas Advanced Computing Center, where we run another very large computer. I guess we'll find out tomorrow what the new ranking of the machine is. I started out in academia doing climate modeling, then spent 12 years in industry working for every other company, SGI, IBM, AMD, and for 6.5 years have been at UT. And I got involved in the black belt program because I didn't have the inside knowledge of the Intel processors, was trying to figure them out and reading the forums. And what got me addicted was seeing people ask questions, and I thought, well, that's a really dumb question. And I'd start to answer it, and I'd say, you know what, that's really complicated. And I really got addicted to the feeling of satisfaction of figuring these things out and helping other people understand.
Great.
I'm James Reinders with Intel. I work out of the Hillsboro office up near Portland, Oregon. And I came up with the title of Chief Evangelist for Parallel Programming for Intel, and so far they haven't figured out what that means exactly. They just keep letting me enjoy parallel programming.
Great. Great. And maybe, James, you could talk a little bit just about the topic today. I think it really is about how do we get the most performance out of HPC and maybe some of the tips and tricks. Let's see if you could summarize that.
I think the topic in general, we call it code modernization,
Yeah.
right? So it's the question of what's the effective way to help software developers take the best advantage of the hardware. It's a pretty broad topic, and it has a very strong practical avenue because so many people that have the science that wants to be done on the machines are not dedicating their career to knowing all the nuances of parallel programming. And so what can we do to make sure that the science is advancing and utilizing the machines with their codes? How can we best make that happen? It's not just purely a computer science problem. It's a problem of much larger scope, I think.
Definitely. And that's one thing I wanted to sort of pull the room here, because a lot of times when I think about an HPC developer, I think of, it is this computer science side of things, but a lot of times it's really not just that. It's there might be some other job titles where computer science or someone who delves in the HPC realm might be a secondary title. And so, first of all, just a show of hands, as far as those that consider themselves sort of experts, either intermediate or an expert in the HPC field here in the room today. Okay, I'd say about half of you.
And none of the panelists.
None of the panelists. I didn't ask them. See, I'm going to ask them lots of questions, so I'm fine if they ignore some of mine right now, just the ones later on. The other one is, how many consider themselves like a data scientist or like a developer, sort of an HPC developer? Okay. Okay, so that's a good sampling, and I think that we've seen that when we looked at the audience demographics of those of you who have signed up for this conference, we saw that we had a very large amount of folks that were either students or in academia, as well as some that considered themselves in some of the line of business versus just saying, hey, I'm a data scientist or I'm an HPC developer. I might be working in bioinformatics or in oil and gas or in the financial services industry, but then also I have to make sure that I'm really understanding the data side of this and the and the compute side. So let's go. We have some questions that we've received from previously. So I'd like to just start out and talk with our panelists and ask them, what does we have these experts here in parallel program. What does code modernization mean to you when you think of modern code? And we like to call it modern code just because that's a desired end state. But what does that mean to you? So, Tom.
I love when they asked us to do that. Because what code modernization means to me is what I was doing for the last 40 years, right? Because whenever you get some new hardware, what do? You need to make things work on that. I guess we can call that code modernization, right? So, but it does make sense to focus on, at this point in time, what are the tips and tricks that we can do to work with the hardware that's out there, right? Which is changing. I was part of the same lunatic fringe that John was. I worked for Control Data, Control Data, Multiflow, Silicon Graphics, and had to make strange computers work in the 1990s. It looks to me like right now we're moving back to those times where we have all sorts of arcane architectures. So what's the big issue with code modernization? I think it is, how do we have things run well enough, not perfectly, but well enough on these architectures so we can move our code from one to the other. Because I can remember the old days where you got locked into a particular vendor and maybe even a particular machine of a particular vendor. And that, what's the term for it? There's a technical term. Oh, it sucked.
So first, I'd like, in a kind of a similar way, I like the word modernization because rather than saying modern, because with the word modern, you run into the same issue that historians have. Okay, we're in the modern era. What do we do after we're in the modern era?
Well, now we're really in the modern era.
No. Postmodern. Wait a minute. Modernization implies it's a process. It's something we need to be continually doing. And I think that there are a lot of really interesting things that are coming back to roost in terms of non-volatile memory and the number of different types of accelerators and heterogeneous computing in general that make how we have been doing parallelism and data partitioning and various sorts of optimization and forward porting of codes different now than it has been. And so I think that it's a really interesting time. It's there's a reason it's a curse to say, may you live in interesting times.
So I think I heard about code modernization when Intel changed the name of the forum from threading on Intel parallel architectures to Intel modern code or something like that. From my perspective, it could mean two things. One that's bad. Modern code means code written by people who don't understand hardware that has too many layers and is terrible. The other thing that it could mean, which I really like, is that you can, in a lot of application areas with the changes in hardware, you can no longer think about parallelism from only one direction. We have, at least in the larger scale systems, have gotten to the point where you can't treat every processor as a separate MPI process because the overheads are too large, so you have to do some hybrid parallelization. The vector widths on the processors keep on doubling 3 times in 8 years. And so a larger and larger fraction of the performance is requiring vectorization. So, and then as we move forward, we have heterogeneous computers, some that are heterogeneous on purpose, and others that are heterogeneous by accident just because of random variability across processors. So there's this extra degree of dynamically self-scheduled parallelism. And so modernization means going back and thinking about your codes in a way that allows you to exploit parallelism in at least 3 or of these 4 different ways.
You know, at first I thought it meant going from 8.3 file names to long file name format. And I think Tom had the same problem. I think to me the big thing is about figuring out what the best, what our objectives are. What does a modern code look like? So what's the best known methods? And sharing those. And I found that there are a lot of knowledge out there, but it's very uneven. And some people look at the task of modernizing their code as very scary because it's really hard. And what I've actually experienced working with people who have had fantastic speedups and stuff is going, oh, I know that technique and this one and that one. And if we share them more, I think it's really helpful. So that's what excited me about getting the forum together. I really hated the name. I've come to love it now, but it's but the idea to me is sharing those techniques, and I think that's going to be very effective at bringing us along. It's not exactly rocket science, although rocket scientists need this.
Definitely. So yes, any rocket scientists in the room. I think one of the things. Okay, we have one. All right. One of the things we've noticed is that we have at Intel, we work very hard to make sure that the hardware and all the systems and the interconnect and the storage and the memory is as fast and efficient as possible. And so when I think of this, I think of all of these types of good things, but also the fact that, hey, that's great. We can do a lot on the hardware and on the interconnect and on the systems, but we've noticed that a lot of times there's just a lot of performance that's being left on the table and a lot of efficiency that's being left on the table by just the lack of maybe doing some coding and maybe modifying the code. And I know it's hard work, but we've seen even with this contest that we just announced last night, we had that speed up that was pretty incredible. We have Matthew Gravy, who's in the audience today, and he was the winner of the Modern Code Developer Challenge as a student. And that's one of the things we're really trying to do is make sure that we're engaging with future developers. And he was able to speed that particular code up by using all the threads and all the codes, all the cores by about 320x. Now, not everyone's going to get that dramatic of a speed up per se, but there is still a lot of opportunity on the table. So I'm going to ask another question.
To be really scared about there?
What?
I heard him up on stage talking to the other student, the other one that got in first place,
Yep.
who joined the contest a week before it ended and did it, and
Yeah.
and then Matthew said, yeah, it wasn't that hard. It's roughly what he said.
Yeah, exactly. And so that's the one thing. We did our contest for 6 weeks. And I believe, Matthew, you took about a month to do his optimization. And then one of the first place winners, I'm sure maybe they had a lot of caffeine and spent a lot of time, but that winner did it in about a week. So
Didn't beat Matthew, though.
yeah, it didn't beat Matthew, definitely not. So I think that's the thing. So as we go through and we're using these techniques, there's things to do with like vectorization or memory alignment or multi-threading. There's some pitfalls, or there's maybe some techniques that maybe have worked in the past, and they might work if all the CPUs are homogeneous, but they might not work going forward. And so one of the questions is, what are some of the approaches that have worked for us in the past, but now they sort of trap us, and maybe some benefits of maybe changing the approach. So let's see. I think, John, you had maybe some insight on that.
Maybe. So in preparing for this meeting, I was thinking about an example code that I've been working with recently. this is a bit of a change for me. I developed something called the Stream benchmark 25 years ago, and have been working in what tend to be bandwidth limited algorithms for most of my professional career. And one of our partners asked me to look at some algorithms that were definitely compute dominated. And it required me to go back and think about things at a very fundamental algorithmic level to try to understand how this mapped onto the hardware. And what I found in working on the Haswell processor with the AVX2 instruction set was that there were certain approaches that the compiler liked and other approaches that the compiler didn't like. And I was surprised by some of them. A lot of times on machines with caches, it makes sense to cram as much into a loop as you can so that there will be data reuse. But in this case, that was a really bad idea because it confused the compiler and it couldn't vectorize or couldn't do any loop reordering. And so I found in this particular case, it did better when I was splitting it out into separate sort of atomic individual updates to the data. In this case, I was doing a sliding average over a long vector, and that involves, if you add up a bunch of points here and you move over one, you've already done almost all of the work, but it's in the wrong place in the registers. And moving data around inside the registers is arcane and confusing. So I spent a lot of time thinking about it and looking at what the compiler did, figuring out what worked and what didn't work. I got about a 12x speed up by vectorization. A lot of it was looking at the vectorization reports, understanding aliasing problems that are often obscure. And then I took another step back and figured out how to do some things that the compiler couldn't do, reusing vectors, full vectors of previously computed data rather than recomputing them, and was able to get another, 9x. So I'm at about 110x speed up without even doing threading. And since this is cache contained, I'm going to get another 12x on our Haswell processor, so 1300 or roughly speaking. But it required understanding the interaction of the data access pattern and the compute pattern in the context of this architecture. And I think this is really important because we are due to double the vector widths again in the next generation, and the infrastructure for moving things around is a little bit different in AVX 512 than in AVX 2. So I think it will help to have the background of having thought through this and thought about all of the different ways that one could organize a group of computations to be able to reuse as much as possible while being consistent with what the hardware is able to do.
All right, thank you. Another question that sort of comes up as a follow-on to this is, what does performance portability mean? And is that real? So anyone have any, anyone want to comment on that?
So actually, don't use the word high with that.
I said performance portability.
So I guess my take on that is performance portability per se probably doesn't exist. What can exist is performance understanding that allows you to write a better algorithm that would be able to give you performance portability. Right now, many of the ways we approach our architecture is just to assume, I'm going to blast this out and hope it works. And we don't actually do a lot in our algorithms to evaluate what the hardware is doing and understand what is available And I think some of that does trickle out, and some of it comes in the numerical libraries and things you can pick up, where you can actually look at some of the counters that are available. You can try to evaluate some of the things that exist on the platform to tell you about efficiencies. And you can build performance portability that way. But if you're trying to do high performance, we've said, you can get performance portability easily. High performance portability is a delicate thing. We're nodding along.
One of the things that I did in my recent exercise, trying to pay attention to this, I was a little shocked. So in most of my career as a performance specialist, I've worked on what you might call benchmarks. So when I'm working on optimizing a problem, it's a particular sized problem for a particular computation. And for this project, I'm working on a library. And I was a little shocked at how many bugs were in my code when I started optimizing it, because it has to work for all of the different sizes that the user might choose to pass in. And even though I had built a testing infrastructure to test my answers, I didn't test every possible input. And as I worked through it, I found more and more cases. I said, oh my goodness, I really ought to back off and quit using heavily hand-optimized code if I don't have to. So I was able to find places where that could get with usually either with coding style or pragmas. I was able to get the compiler to do certain portions of the calculation at 95% of the speed of my hand-coded version. And that way the compiler took care of all of the alignment checks and all of the array bounds. But there were other pieces of the code where maybe somebody knows how to get the compiler to do the transformations that I need, but I couldn't figure out how to do it. But I tried to limit the ugly manual coding to the parts that gave a really big performance benefit.
Because those are the parts you're guaranteed to have to change later.
Yeah, actually, these parts do include explicit use of AVX vector intrinsics, and those are going to be a different width in the next generation. So yeah, that part's going to have to be rewritten.
All right. Thank you. The next part is, can I write, if I'm writing some code, can I really write once for a GPU and a CPU and get a maximum performance for both?
No.
No.
Why not?
Next question. Because the GPUs, I think a GPU is what I would call a restricted architecture, and I think I mean that in an engineering sense. When you're designing a compute device, you've got different avenues, and one of the choices you can have is to restrict what you're capable of doing, and then see what you can do with the design. Xeon Phi took the route of not restricting what instruction set we did, but saying we're going to assume you're a parallel program. And that's what makes it different than a Xeon. So we threw out a bunch of stuff that would help you a whole lot run a serial program, and people complain about that all the time, but it's like, well, that's what Xeon Phi is. And it's very interesting, and we've had accelerators through the years, different designs that take this avenue of, hey, maybe I can compute certain things really fast if I don't try to do everything. But if you try to do everything and be high performance, well, you get a Xeon, or you get something different than what you get with a GPU. And so the concept that you would write it just once somewhere. The other big thing with GPUs is GPUs excel at expecting latency to be hidden. And when you start writing code assuming that you've got enough parallelism that hides your latency, you're writing a different style than you would write generally for a CPU. And so they don't converge, and I don't think they converge on purpose. If they did converge, then you've actually engineered devices to do the same thing. So you haven't exercised your range of latitude that you should have as a hardware designer to design different compute devices.
Okay, so you can get them to run on both. but not necessarily get maximum performance out of both,
Not
right?
with the same code, except on matrix multiply, maybe.
Yeah, okay.
Simon's not here, is he?
That's a library call.
Exactly. Here you should.
Programming language issues that are
Yep.
very different.
Okay, and then what if I add like FPGAs to the question?
If you can program an FPGA, we'll hire you.
Okay.
So, so an FPGA, what really surprises me about FPGAs, I look at FPGAs as a hardware designer as just a wonderful box of cool parts. It's like Tinker Toys. I can build anything I want. And at a very small scale. But the concept that you're going to program them with a high-level language is pretty funny. And there's a lot been made about OpenCL for it. And I think OpenCL for FPGAs is brilliant, but I think people don't understand why it's brilliant. FPGAs, there's a lot of challenges programming at what I'd call a control level of programming, moving around parts of your code, moving the data. And OpenCL does that, and people, I think, make the mistake of thinking that when people talk about programming FPGAs and OpenCL, they're talking about programming it, coding it like a normal program, and that's not quite what's going on. And I think FPGAs are extremely exciting, but I think we're a long ways off from them being truly reconfigurable computers that just get programmed with arbitrary programs, but they're still really cool.
Okay.
I'll get some opinions here.
Here.
So I guess you could mute the mic if you don't want to hear this. I was the I was the strategic technology lead for accelerated computing at AMD from 2006 to 2008. So I worked in this area. FPGAs are very hard to program. It's a completely different mindset. It's essentially that you're building a data flow engine. And that's the way I see OpenCL as linking into it. You create a function that has input data streams and output data streams, and then you extract that function from the CPU and you put it on the FPGA. And FPGAs have a fairly narrow window of applications that can be mapped to them because you're communicating with it over an I/O bus, PCI typically. Some changes in the future from Intel that I'm looking forward to very much. But you need to have a computation that has enough work to do that you justify moving the data off of the processor chip and back. And typically a PCI interface has about 1/8 of the bandwidth of your DRAM interface. So it's a lot more expensive, but the problem has to be small enough that you can actually fit it inside the FPGA. On an FPGA, you're not writing general purpose code that can do an arbitrary number of computations. Instead, you're sort of looking at a data flow graph and actually creating a multiplier for each node in the data flow graph that has a multiplication, and creating an adder for each node in the data flow graph that has an addition. And you can do on the order of 100 of these on a very large, expensive FPGA. But if your algorithm naturally needs more than that, then you have to step back a level and either cycle it through on the FPGA or do something else. So it's kind of narrow. There are some things that FPGAs are incredible at. At TAC, we are now having an FPGA system installed. It's a Microsoft system that they developed for their Bing search engine. FPGAs are wonderful at dealing with bits because they basically give you very small lookup tables. They give you tens of thousands of small lookup tables that you can connect any way you want. That can be used to do arithmetic or search or all sorts of other features. But I think the big thing is just the mindset of doing more data flow oriented programming is so different than the mindset of doing control oriented CPU programming that it's very challenging to bridge that.
And I have a very simple mind. to me, it's like having a skateboard, a VW bus, a Ferrari. They're all vehicles, can go someplace, but each one by its hardware nature is useful for different purposes. And that's part of discovering for each of these, on what kind of device does your problem lay down the best? Or if you have certain devices, you're going to have to figure out, is there different algorithmic changes that'll help your problem lay down on the hardware you got?
Okay, great. Thank you. So one of the next questions I want to ask is around some pain points. So, maybe some pain points or some challenges that you've seen, and maybe how you've overcome some of these pain points when you've been developing in this domain. All right.
Matt is the
So-
master of pain.
Yeah, I am the master of pain, evidently, since that was the immediate reaction. So there was kind of, again, in the preparation for this, there was one story I was relating, and I think this ties into exactly what we were just talking about, that there's I hate the phrase flops are free, because that's not the right way to think about the modern age of computing. But it is true that many of our codes have moved where being bandwidth limited and being latency limited is more and more of an issue. And one of the things I've been doing a lot of work with recently is specifically around the bandwidth limitations that come from I/O intermixed with the normal MPI communication. And so we were running on some of the Oak Ridge machines, and we're noticing a relatively significant decrease in performance of the code. And we design I/O libraries, and that's a whole other fun conversation, where we basically trick people into thinking they're doing I/O when really they're doing messaging and pub/sub infrastructures. And we found that we had to very consciously schedule on a server-side I/O approach all of those messages, because if we ran the message at the same time that the application was trying to do an MPI all-to-all, that the jitter in the delivery of those MPI messages caused a 30% slowdown in the execution of the main code. And obviously that's bad. So we went through, we came up with a nice way where we could actually predict where those MPI all-to-alls were going to be. We did a distributed monitoring solution so that I could only fetch those messages when I knew you weren't using the network. And then we went back and so we got that overhead down to something right about 2.5%, 3% for total I/O on the code. And we went back and remeasured what the POSIX I/O, which had originally been in the code, was doing. And POSIX I/O is supposed to be completely blocking. So there should have been no cost associated with it. It blocked the code, so that slowed it down a little bit, but it shouldn't have impacted the MPI calls. And what we found was that wasn't true, that there was enough going on in the OS where you'd blocked in order to buffer the memory, but that the OS on the individual nodes was still trickling that data back to the I/O servers on the back end during the MPI calls, that a blocking synchronous call was still causing problems on the overall performance of MPI. In finding these sorts of issues around bandwidth management, all of this goes down to the OS was completely ignorant of bandwidth management, and so was not thinking about flow control at all, because it was just focused on timing and CPU utilization.
Maybe you can, when I worked in industry, my work was on lab machines, which were mostly reserved for the benchmarking team. I moved to the University of Texas, and all of a sudden I was sitting behind 60,000 core production machine and discovered that the order one term in the performance equation for that system is the system running? And so the staff is very sensitive to things that cause the system to not be running. And what I've learned in my time watching is that the I/O system is very often the most delicate piece of the system. One thing that I have a great deal of trouble with I/O is just figuring out where the stuff is going. For a given user application configuration, how does that map onto the hardware and to the file system metadata servers, the file system data servers, all the various InfiniBand links that map all of these things. So our number one support issue is when people start abusing the file system, the head system admin blocks their accounts, and they file a ticket saying, my account doesn't work anymore, and we talk to them and work them through the steps so that they quit doing that, and then we unblock them. But do you have any experience with any sort of tools that would help you see or understand, anticipate these sort of limitations?
There are some tools out there, and there are some well-known issues that don't have a good way to deal with them. One of the issues is that our job schedulers onto these big machines tend to be focused on how do I dense pack a certain number of cores or processes into a part of the topology. They tend to be completely ignorant of what's the impact of that dense packing on actually getting data out to storage. And so we've actually done a number of studies where you can pull out that topology and you can pull out the kind of real-time traces, and you can see that, I've got this clump over here and I've got this other job here and the IO's over here, and I can watch this pipe of data moving through to the IO, and it slows this guy way down. And just that degree of variability that you get in performance because of this architecture is really kind of shocking, how much people have tolerated. So you can build those sorts of visualizations and you can understand it. I'm not aware of anybody who's really put all of the tools together to be able to watch that in real time and control it. And I think it's a great area of possible expansion, and certainly would love to see the Luster folks look into being able to expose more of the way the OSTs are being used, because that architecture of how I'm doing striping across all of those storage targets is important. I'll say the other personal research bugaboo is we need to stop thinking about POSIX file systems as the right way to do high-performance computing I/O. It's been a stupid idea for at least 15 years, and it's going to, there are only so many times you can shoot yourself in the foot. And hopefully we've almost hit that limit. So.
Right. or Tom has something. Mine's a simple one. It was when I was a child at Control Data, and I realized that the focus on just getting CPU performance, well, I/O mattered. And you're both echoing the same thing. But that was a revelation to me, that how I move data around could affect my overall performance. And what I realize is we're still in that time frame now where data motion is really, really important, because CPUs are speeding up faster than our memory systems. So in the future, it's going to be, I think, more and more of an issue on how do we move data around. Is it worth moving data and transposing it? Clay Brashears has an example that he loves when he was tuning, where he had complex data. Well, it was real, imaginary, real, imaginary, real, imaginary, real, imaginary. Well, how did he get his speed up? Put all the reals together, all the imaginaries together. There was data motion involved, but he had enough work behind it that it amortized that cost of data motion. So I guess that's the big one. Learning how to amortize data motion is good. And if you can simultaneously hide your data motion by having enough compute behind it, I mean, that's a real art form to do them simultaneously well.
All right. Hey, I want to thank the Black Belts for coming and joining us today. We hope this was a conversation that spurred some thoughts and spurred some new ideas for you. How do we continue the conversation? Well, we have a place. One of the questions is, hey, how can Intel help me go forward? We have the Modern Code Developer Program. We actually have an online community here of HPC experts, training and content, very good training from Colfax and some of our other partners, promotions, where you can get a Xeon Phi and Parallel Studio license at a discount, and then of course our products, including some of the tools and products. And then we have challenges from time to time that we will run. So really just like to thank everyone for joining us. We'd like to continue to have this conversation with you. We actually have a booth here. Come and join us or come and see us at the booth. And we have some goodies for folks that stop by. Of course, we have this goodies to reiterate for tweeting. And then we actually have a simplified Rubik's Cube as well. The idea here is to simplify parallel programming and simplify the code modernization. So,
James is going to hit you.
James, do you have any closing words here?
No, I think we're good.
All right. Hey, thank you.